Okay, so I got to record back on, share application. I want the Chrome tab. There you go. Share. Huh. Okay, I give up. Well, just pop. You guys seeing it now?
No.
This tab is sharing your screen. God, what am I doing wrong? Well, I got a big problem. I don't know. I'm having some really big problems. Now I have this. I don't even have to see that. Let me stop sharing and see if it goes away. Am I back?
I see the board.
Okay. Let me see if my chat can work. I don't. I really don't know. I'm kind of at a loss right now because everything's just running slow. Maybe a million people are using the internet now. Okay. Well, do you see that link? You guys see the link?
Yeah.
I just sent it through chat, like I think it was Ethan said. Do you see it?
Yeah, I got the video pulled up.
Okay. You guys, I'm gonna wait a few minutes. Go ahead and look at the video on your devices. It's about 4 minutes long, and I'll just pause for a minute. Go ahead and watch it, and then we'll come back in about 4 minutes and we'll talk about it. So bring that video up, take a look at it, and I'll come right back. Okay, guys. Hopefully, if you watch the video, the first like 3 minutes is the most important part. So go ahead and finish it up and come on back to the session, and let's just talk about what happened in the video. So I'll give you a second to just finish it up, and then I want to talk about it. Now, this is Faraday's law. And let's talk about the video. So in the video, the gentleman in the video had a magnet. He had a coil. He had actually several loops of wire. He had a coil that had one loop. He had a coil that had 10 loops. He had a coil that had, I believe it was 100 loops. And he had a special kind of ammeter. If you notice, the ammeter kind of, the needle set right in the center. The zero was in the center. And the thing could deflect either to the left or to the right, showing current magnitude and current direction, which is kind of cool. Now, even though in the video he talked about current, remember the cause of a current is a voltage. It's a cause and effect here. So really what he did, he talked about creating current, but really what he did, he created a voltage. And that voltage, we use that voltage to move electrons and create the current. So really what he created was a voltage. Now go back to the third week of class and we talked about voltage. For the second week of class, we defined voltage. You know that voltage is a separation of charge. And we talked about DC circuits, of course, now. So the only way you know to get that kind of a voltage is with a battery. Batteries separate charge. And anything that creates a voltage basically separates charge. So battery will separate charge. There's electrochemistry involved there. But here we have a mechanism where we have a magnet and a piece of copper, a magnet and a coil of wire. And through forces, electromagnetic forces, we can actually cause electrons to separate from the atoms and be moved to one end of a conductor. I can cause a separation of charge by providing a force on electrons that are free to move and kind of stripping them away from the atoms. So here's a totally different way of creating a voltage, and I can use that voltage to separate charge. Now you'll notice in the video a couple things. First of all, the loop that he had and the magnet, if he basically moved the magnet in and out of the loop, right? And you saw that. He could have held the magnet stationary and moved the loop. It doesn't really matter which one's moving. It's just you gotta have two things. You gotta have the coil, and you gotta have magnetic field. And so the missing ingredient, the third thing you gotta have is motion. And so I was saying that in the video, he held the coil stationary and he moved the magnet. He could have actually held the magnet stationary and moved the coil. There has to be relative motion between the conductor and the magnetic field. If you do that, you create a voltage. Now the problem is that I gotta keep this motion has to be continuous. So what you saw in the video, when you moved the magnet into the coil, when the motion stopped, the needle went back to zero. So we moved it in and the needle deflected and went back to zero, but when we pulled it out, it deflected again, but this time the other way. And if you kept moving this magnet in and out, or if you kept moving the coil across the magnet, what you will see is the ammeter go back and forth like this. That's indicating that there's a voltage, that there's a voltage creating a current, and the current magnitude is starting at zero, going to a maximum, and then going back to zero, and then changing direction and going to maximum in the other direction and going back to zero. So if he kept moving the magnet in and out of the coil, you would see the needle do this, alternate back and forth. And this is why I start with this video in AC. because it's basically the essence of alternating current, alternating voltage. But let's just talk about the video, and we'll stick with it. But I'll come back in the AC. It gets to be really interesting. Notice in the video, though, he started with one loop in the coil, and there was a slight deflection on the meter. He added more loops. He took a second coil with 10 loops, and there was more deflection on the needle. And then he went to 100, and with about the same amount of motion, there was a huge deflection on the meter. So he was trying to show two things. Number one, the amount of voltage created, or the term we're going to use for this voltage created in this fashion, voltage created using this electromagnetism, is called induced voltage. And so this induced voltage is related to, number one, the number of turns on the coil. The more turns on the coil, the more voltage is created, which can therefore create more current. So that's the first thing. The other thing he mentioned was the speed at which the magnetic field moves in across the coils, the speed at which basically the magnetic field cuts across the coil, that speed is related to how much voltage is produced. And so I don't know if you watched it all the way through, but he gave you, I think at the end, I never watched it towards the end, but let me show you mathematically what this looks like. Now, if you know calculus, some of you had calculus before, we'll write it like this, that the induced voltage, so we'll call this induced voltage, induced voltage. That's not a voltage created by electrochemistry like a battery. Here's a voltage. Here's a separation of charge created by basically electromagnetic forces. And so this induced voltage is equal to N. Well, that N, for my Faraday's law, I got to have a coil. Well, mathematically, we're going to use an N to represent the number of turns on the coil. And then he had this other thing. I'm going to write it like this. If you had calculus, now remember this right here, he said that was flux. That's magnetic flux. So he had this, you'll see it written this way. So there's a flux with a D in front of it. And then on the bottom, I have another D and a T. So if you had calculus, you know what that is, right? So this is a rate of change. This represents a rate of change. And this is when I have T, this is time. When I have T in the denominator of a rate of change, we call it a time rate. You've seen time rates before, because when we talk about power, we said power was change in energy over time. So that's a time rate of change. So time rate of change is really special in physics. So if you had calculus, you see it written this way. If you didn't have calculus, it's okay. You can think of this thing right here. You've seen this delta operator before, the change in. So you can also write it like V induced is equal to the number of turns on the coil times the change in flux over the change in time. So let's think about, either way you think about it, they're pretty much the same. But either way you think about this, let's write out relationships. Let's look at how these are related to each other. Well, first of all, the induced voltage is directly related to the number of turns on the coil. So V is directly proportional to N. So he showed you that in the video. He added more loops, got more voltage. He didn't show you in the video this or this. V is also directly related to the flux field. In other words, he could have got a stronger magnet with more flux lines and moved it at the same rate, and he would have gotten more voltage. So V is directly related to the flux. It's directly related to N. Now, think of this fraction right here, this whole fraction. This whole fraction. Well, obviously, over here, You need some kind of magnetism, so the magnet is represented by flux. So that's that one. But you know, there's also motion. How do you represent motion mathematically? And you do that with the time rate, a time rate. And so this thing in the circle here, that represents motion. The faster I move it back and forth, the faster those flux lines cut across the coil, the bigger this whole fraction is going to be. So you can also think about the voltage being directly related to delta phi, the change in flux over the change in time. So I got a couple different ways to produce more voltage. Either way, anyway, if you take just any one of these away, any one of the three off the list, you can't induce a voltage anymore. Now this is actually pretty cool because if you think about it, you don't need any chemicals. You don't need any. All you need to do this is a conductor and a magnetic field. And this is what I call generator action. Generator action. If you remember, and I'll just go briefly into this because we go real deep into this in the AC. I don't want to spend too much time, especially since I screwed up the time trying to show you the video. But let me just talk a little bit about, remember the motor action. I won't draw the diagram from before, but basically what we had last video or last lecture, if you think about it, we had a fixed magnet. We had two magnetic poles, a north and a south pole. And anytime you have separated magnetic poles, between the poles, you have flux. So we had flux. Now I drew it a different way last time, but it's the same idea. I think I had a magnet here and a magnet there, but it's the same thing. So here's my flux. And then what we did is we took a conductor and we bent it into a coil like this. And then we hooked up a battery to this. Here and here. And we talked about strong and weak fields. And through the interaction of those strong and weak fields, we're putting in electrical energy, and what's going to happen, this thing is going to spin. Now, you know what's going to happen. These wires are going to twist and break. But in AC, I explained how this thing is actually constructed and how we get around the wires breaking, and I'll go into detail of this. But that's not what I'm trying to show you. I'm trying to show you that if you put in electrical energy, what you get out is mechanical energy. You can put a shaft over here and connect a pulley to it, a fan, a motor, whatever you want. You change electrical energy to motion, electrical energy to mechanical energy. Well, Faraday's law is the opposite. Because if you think about it, let's say I disconnect this. If I spin this, I have everything Faraday says I need to induce a voltage. I got a coil. I got a magnetic field. And if I'm spinning, now how do I spin it? Well, again, I can put a shaft here. I can put a shaft right here. I can put a pulley on it. In your car, you have a generator in your car. And that generator has on this end a pulley, and it has a belt over it. Or maybe I have some blades here, and I can stick it up in the air and let the wind turn. Some kind of way I got to spin this thing. That gives me my motion. But I have everything Faraday says I need here to induce voltage. I got the conductor, I got the coil, and I'm spinning this. So when I get on the outside of the same machine, I get electrical energy. So what I'm saying is a basic generator and a basic motor, same machine. It just depends on what you're putting in. If I put in electrical energy, I get out mechanical energy. This thing will spin. If I put in mechanical energy by spinning it, I get out electrical energy. Same machine, just depends on what the input is. So when I refer to motor action, what I'm really talking about is Faraday's law. All right, so this is pretty important. Again, I don't really drill down into the details of this, but in AC, I start with this and we go into the details of how this thing is made. We talk about how the wires are connected. We talk about the type of signal that's produced and why the signal is what it is. So I spend a lot of time talking about that stuff, and probably most people that teach the course will just jump right to the AC portion of it. But I think having an understanding of this, what's under the hood of the car, I think you'll appreciate AC a lot more. So when I teach AC, I go into this, and it's pretty interesting. So, but Faraday's law, you can bet that'll be on the final exam. So if you have that one handout, the practice problems, there were a couple practice problems. I know we haven't looked at this sheet in a while. This says circuit analysis 1, magnetism practice problems. If you have that sheet, take it out. I think we did the first two already. The first one was we had a magnet. It was 40,000 Maxwell's of flux. We had to convert it to Webers. And then number 2, we had 25 microwebers. They gave us the area. We had to figure out the flux density and Tesla units. But I want to look at number 3 and 4. So if you have that sheet, take it out. It's online. You can look at it. Or I'm not going to write the question on the board, but I will read it. So give you a second to find that sheet. I'm going to clean the board up. We'll do a couple calculations. And I think that's probably all I want to do today. I'm kind of, that technical difficulty put me in kind of a bad mood. Mess my video up. But I do get to see what happens when because I disconnected and I went back. We'll see how that works out with that recording. I'm interested in how that goes. I guess it'll just pick up where it left off. I don't know. We'll see what happens. Okay, let me read the problem. You may not have the sheet in front of you. Now, what we're going to use is Faraday's law. So Faraday's law. Now, I'll write this like this. But when you take me for AC, I'm going to use a little script V like that. Because the voltage that's produced is really what we call an instantaneous voltage, which produces an instantaneous current. And in AC, the way you write a letter makes a difference. In AC, this is like a continuous current, but if I write it like that, it's an instantaneous current. This is a power. This is an instantaneous power if I write it like a script. So I'll do it this way, but next semester if you sign up for my class, we'll change to that. But anyway, that's not important right now. So we said Faraday says that induced voltage is directly related to the number of turns. It's directly related to the flux. I won't use the calculus notation because some of you, it's the same thing though. It's a change in flux over. I'm just going to put time here, but you can put a delta T down there if you want. The change in time always starts, T, let's say T2 minus T1. Usually you start time at 0. So it's not like when you have, Y2 minus Y1. But here, if that's 0, you got 0 minus, you just get T. So I tend not to put the delta on the bottom, but some people don't like that. So there's a change in flux over change in time, but we started at 0 time, so I'm not going to put the other delta in there. So there's our formula. Let me read the question. The question is, it says you have you write this down if you don't have a sheet. Please write it down. You have a magnetic field cuts across a coil having 2,000 turns at a rate of 2,000 microwebers per second. I want you to calculate the induced voltage. So let me write down what's given. So it says you have a magnetic field cuts across a coil having 2,000 turns. So that's this, the number of turns. So N is 2,000. Now, when I use this formula, the unit is a turn, but just treat this as a unitless number. We'll just say 2,000. N is 2,000 because we're counting things. A magnetic field cuts across a coil having 2,000 turns at a rate. So now we're talking about this thing. A rate of 2,000 microwebers per second. So if I just look at this is my time rate of change. So it's saying that the change in flux over time is 2,000 microwebers per second. That's change in flux, change in time. So this is the way I would write this as a ratio. So just plug that into the formula here. I get 2,000. That's my number of turns. And then this fraction right here. Now, when I do this, I just like to, I write it as 2,000. And I'm not going to leave it like that. I'm going to say 2,000 times 10 to the 6. And I like for this to be in Webers per second, not micro. I don't like using it like that. So it's 2,000 Webers per second. But it's micro Weber, so I got to put the negative sign there. So when you smart guys with a calculator, I got 2,000 times 2,000 times 10 to the minus 6. My answer is going to be in, we're just going to jump to the, normally I'll show you how these units cancel out, but the answer is going to be in volts. So if you take 2,000 times 2,000 times 10 to the minus 6, give me my final answer in volts, please.
4 volts.
4 volts. 4 volts. So here's a way to produce electricity, no battery. All you got to do is have a magnetic field, you have a coil or some kind of conductor, and just using motion, you can create electricity. I actually show you, and I don't know if I'll show you since we're doing this remote stuff, but I actually have a clear flashlight. You guys are probably seeing the flashlights that you can shake up and down, or maybe the radios that you can charge them up by cranking them based on Faraday's law. And I actually show you, I have a flashlight that's clear. You can see the coil, and there's a little tube in there, and in the tube is a magnet. And when you shake it up and down, that magnet goes up and down through that little column and cuts across the coil and charges up either capacitors or a little rechargeable battery, and then it lights up these LEDs. So you've all seen those flashlights that you can charge like this, or the radios that you can crank. And even if you have a, what do you guys call those? The thing where you can, a cordless phone charger. You can just set your phone on top of it. You never plug it in, you just set it on top of it. Well, in AC, I tell you, explain to you how exactly does that work, and you'll see it's based on Faraday's law, exactly what we're doing right here. Same thing. Once you understand this, a lot of things are going to become crystal clear to you once you get used to thinking about Faraday's law the right way. So I think 4 volts is the right answer. Let's do this last problem, and I'm losing my voice, so we'll call it the day after this, unless you guys have some questions. So here's the last problem on the practice sheet, and what do we? Oh, okay. So we're running out of topics. We do this and inductance, and then we're done. That's the semester. So I got to go back and look. We might be moving too fast. I don't know. How many more days do we have? We got all of next week, and then
Until the 4th.
okay.
So just
It's basically, yeah, it's basically just next week.
Well, we'll be done a little early then, because I got this lecture. We got to talk about inductors, and that's it. And yeah, so we'll be done. We'll see. I don't know. I'll get moving on a tangent here. Let me read the problem, because you guys want to get done with this stuff. Here's the problem. A coil of 1,800 turns has an induced voltage of 150 volts. I want you to calculate the rate of change, d phi dt, or delta phi delta t, however you want to write it. Calculate the rate of change in Webers per second. So I'll read it again. You have a coil. The coil has 1,800 turns, 1,800 turns, and the voltage induced by the coil is 150 volts. They want to know the rate of change of the flux in Webers per second. So write out what you know, write out what you're looking for, and then we'll use this equation to solve it. And I'll go ahead, and while you guys are doing it, I'll put it on the board. So we have a coil has 1,800 turns, so I'm going to put it over here. That's N. N is 1,800. And they give us the induced voltage. V induced is 150 volts. What we want to know is d phi dt. Again, this is the time rate of change of flux, or our delta delta phi over delta t, whatever one you want to use, but we want to know this part. So treat that as one number, you solve it, and then we're done. So treat this thing right here as the unknown, and then you're good to go. If I treat that as the unknown, if I want to find x here, I got to take my v induced divided by n. So v induced divided by n is going to give me x in this equation, but the x is really equal to d phi dt. So v induced was 150, and what was my n? My n was 1800. So what we're solving for is the time rate of change of flux. So we're solving for what's in this box. So what is 150 divided by 1800? What is that?
0.0083333.
You said 0.08?
Yeah, 0.0833 repeating.
So I'm going to do that. And then, so the units, we're not going into the unit thing. We don't have enough time to do that. But this would be we're going to use the MKS and not CGS. So this then for us would be in Webers. Of course, time is always in seconds. So for here's the one time you're allowed to just throw the units in there. So we got 0.083 Webers per second. That's the rate of change. And of course, they would probably write it as milliwebers, but I like to leave it out as the whole unit when I'm using stuff like this. So there it is. Faraday's law is simple, but I think when you guys take AC, when we talk about this in AC, it's simple, but so many applications is mind-blowing. And without Faraday's law, we'd be living in the Stone Age. And you'll see that AC is going to help you to see a lot of different things, and I think you'll be pretty pleased with it. So that's it for today for the material. Anybody have any questions about the material? Anything we talked about today or last class? Any questions about it? I'll take any other questions. I'll turn the recorder off in a second. But anybody want to talk about anything that we talked about today or last class or any of the magnetism stuff? Okay, let me turn my recorder off, and then we'll see if anybody has any other questions. So stop.